Welcome to the lecture on Bayes rule. In this lecture, we will explore what Bayes rule is about and what are its applications in science, engineering, and in the modern artificial intelligence techniques. Before going to the details of Bayes theorem, we will first consider an example where it gives rise to the Bayesian analysis or the Bayes rule. Suppose you know a process, let's say bad air quality, then you know in an area there are several factors contributing to the bad air quality, such as pollution from vehicles, pollution due to construction, or stubble burning. Now, all these factors are contributing to the bad air quality. Now, if I reverse this question in such a way that you on a random day observe bad air quality. Now you have some prior knowledge that the factors affecting the air quality are vehicular pollution, construction, and stubble burning. And the proportion of each of these variables is the prior knowledge we have. Now, on some day you observe bad air quality and you are staying some part of the country and you don't know with which factor it's caused. Now, your goal here is to identify what is the likelihood, the probability that the bad air quality today is due to the vehicle pollution, or it's due to the construction, or it's due to the stubble burning. You have the evidence only that you are observing the bad air quality, and you have the prior knowledge that these factors lead to the bad air quality. But at the present, you don't know which factor has contributed to this bad air quality, or what's the likelihood that it was caused due to the vehicle pollution, construction, and stubble burning. Now, this is where we want to find the reverse probabilities, and for that, Bayes' theorem helps us to do that. But before actually going to the formal definition of Bayes' theorem, we need to understand some concept called the conditional probability. So, what is conditional probability? Suppose you have two events A and B. Both the events have some positive probability. Now, suppose an event occurs, let's say A event has already occurred. Now, your goal is to find what is the probability that event B will occur given that A has already occurred. So, in order to find the probability of B given that A has already occurred, we have the concept of probability of, we first find the probability of intersection, that what is common between A and B, to the probability of what is the probability of occurrence of A alone. Now in this case, you can obtain the probability of joint probability of A and B occurrence together is that probability of A times probability of B given A. Now you can also do the same thing with probability of A given B, probability of A given B. This, with the same way, we can have probability of A and B together to the ratio of probability of occurrence of B alone. Now from here we can also obtain the probability of A and B occurrence together, which means these events occur together. This we can obtain as the product of probability of occurrence of B times the probability of A given B has already occurred. Now from here and from here, we can see that on the left, both of the equations left side we have probability of occurrence of A and B together, and on the right hand side is in terms of probability of A and its conditional probability, and probability of B here and the conditional probability. Now we can equate both the things because on their left side is the probability of A given B, A and B occurrence together. So we get probability of A times probability of B given A This we can equate with the probability of B times probability of A given B. Now, any one of the sides we can choose, and we transfer one of the terms, then we can obtain that probability of B given A is equal to probability of occurrence of B alone times probability of A given B whole divided by the probability of marginal probability of A. And this, my dear friends, is a form of Bayes formula or Bayes rule. But what it helps us is finding the probability of an event. Given that another event has already occurred, we can find that with the help of individual probabilities and their likelihood. Now, in order to formally define the Bayes theorem, we need to understand, we can formally define the Bayes theorem as from the above formula in terms of causes and effects. Now, suppose that you observed some effect in our example, let's say the bad air quality, and you want to find with what is the likelihood that the bad air quality was due to let's say vehicular pollution. Then you can calculate that by knowing the prior probability of the cause, which means the contribution of the vehicular cause and its contribution to observing the effect, that's the air pollution, bad air quality. Then we call that the likelihood, and we divide that with the probability of the marginal effect called the marginal likelihood. Now, this is where the Bayes theorem helps us, and it has so many applications in artificial intelligence or in some other diagnostic settings where we have some prior knowledge and the likelihood of an event. Then with that we update our belief, what is the probability or the likelihood chance of that the particular effect was due to a particular cause. So this is Bayes theorem. Now we need to understand another setting of the Bayes theorem, that an evidence need not to be a single evidence for a particular event. So there may be multiple events for the occurrence of an event. To understand that, we will first define partition of a sample space. A set of events E1, E2, En is said to represent a partition of the sample space S if EI intersection EJ is empty. That means they are pairwise disjoint, there is nothing common between them, and their union is the whole set. That's they are exhaustive, they are constructing the whole set when they are joined together with the union operation, and the probability of each event is positive. There is a non-zero possibilities or probabilities of these events. Now the whole sample space can be divided with with these disjoint sets we call later in our setting as evidences for a particular effect. One simple one simple partition is just you have a set E or the evidence set and elements which are not in the evidence set together with all together these things construct the whole sample space. So this is the simplest example of a partition. So why do we need this partition is that we need to obtain the event A as the union of all these things. So a set an effect may be observed and it may be having certain factors contributing to it, as in the case of air pollution it may be due to vehicle, it may be due to the construction, and all those factors are contributing. So we need to sum up all these events. So law of total probability says that if we have an event A and we have a partition over the sample space S, and this A can be seen as the collection of all the parts which are common to it and to the evidences EIs or the partition EIs. Now A can be written as the union, which means the union collection you are collecting the common part of A and evidence EIs. So with the first we have this part common, with the second we have this part common, and all these are actually uh, giving us the whole A. So if we have to calculate the probability of event A, then we can do that with the sum of the probabilities of these individual events, and they are disjoint, so their probabilities are added. Probability of intersection of any event EI with the A, that is a joint probability of these two events, which means that we have observed the effect and it was due to a particular evidence. We can do that with the conditional probability. We observed that we have probability of EI times probability of A given EI. This gives us the joint probability. Now this joint probability can be used to obtain the whole probability of our event of interest. In our particular example, that was about the air quality, and we want to check whether which factor was contributing more to the air quality, bad air quality. Now let's recall the Bayes theorem. What it says, that probability that the the posterior probability, which means the diagnostic or a prediction of effect A which we observed, is due to the evidence EI, is what is the prior knowledge we have about the evidence, and what is the likelihood or the reliability of the evidence to that cause A, and what is the overall likelihood of that event A. So we can write A as the sum of the probabilities or due to different evidences. Now where is the application of this in the modern science is that we build with this Bayesian settings, we build classifiers. In AI we call the naive Bayes classifier, and that filters, let's say, emails in your Gmail account or in any of the accounts. You have a email classifier which sometimes sends some emails to the spam box and some legitimate emails also to the spam box. So this model is a probabilistic model. It can make mistakes. That's why you always check spam folder also when you are waiting for an important email. And industries or the companies also suggest to look at the spam folder, because the classifier in your account is sending sometimes your legitimate emails to the spam folder. Since the model is probabilistic and due to certain evidences or due to certain characteristics in an email, that may go into the spam folder. So we have certain spam emails, and based on that we build a classifier which tells us about the nature of incoming emails. We will solve one example from the medical diagnostic setting. Suppose that the reliability of an HIV test is specified as follows. Of people having HIV, 90% of the test detects the disease, but 10% goes undetected. And of people free from HIV, 99% of the tests are judged positive, negative, but 1% are diagnosed as showing HIV positive. From a large population, only 0.1% are having the HIV. Only this much person, and with this information, a test is performed on a randomly selected person, and he receives a report from the pathologist as HIV positive. Now, our job is to find what is the probability that the person is actually having HIV. His results are showing HIV positive, but the reliability of the test is given. With this, how can we tell what is the likelihood that the person is actually having the HIV positive? Now, if I write down the H as the set of all those people which are having HIV, and then H complement will be the people without HIV, then these two sets are the partition of the whole space. Now, I denote positive as a person got HIV positive report and negative as a person got negative HIV report. We are given the information that if a person is belonging to the HIV positive people, then the test will detect it with 90% of accuracy. That's given. And 10% goes undetected, which means a person from an HIV uh, set, which means he is having HIV virus, then the test will denote that the person is not actually having the HIV. It's about 0.1 probability, which means 10%. And it's also saying that it 90%, 99 times it detects that people are with who are without HIV, they are actually without HIV by the test. And sometimes it makes mistakes with the 1% uh, that people are who are not having HIV, they are given as the test report as HIV positive. We are also given that only 0.1%, which means 0.00 probability of H, which means this much amount, this much probability is for the people with HIV. Now, our goal is to find the person who got the result as HIV positive. This we are given. How likely is that he's actually having the HIV? So we can denote that with given that we are having the test as result positive, what is the likelihood that he is having the HIV positive virus? So we can write it that by the Bayes theorem as the prior knowledge of percentage of people with HIV and the likelihood that a person who is HIV is actually having the positive test, and the test being positive irrespective whether the person is having HIV or he's not having HIV. This we can write as people with who are getting the positive results, they may be those people who are also having negative but the test shows positive. So this is the way we have contribution from both positive and negative for the test positive. So if we calculate this probability is we get 0.083, that is about 8.3% of the chance that the patient is actually having HIV. So if you receive a test from a laboratory and you see some discrepancy, so don't be panic. There may be a wrong result coming from the laboratory. Now we will go into the setting of how Bayes theorem can be used in making many inferences. So if we recall the Bayes theorem, it says that a posterior probability that the updated belief about a particular event is how likely that effect is due to a cause, and the probability of the prior probability of that cause, and the effect of the probability of the effect, the marginal likelihood of that. This is by the Bayes theorem. If we simplify it, it says that the updated belief is proportional to the likelihood times the prior information or the prior knowledge we are having. Now, how Bayes theorem helps us in making the inferences, like in the HIV case, we have an example of M as having meningitis and S as a stiff neck. Suppose these are the two uh, characteristics a person is having, and our job is to predict how likely is that if a person is having a stiff neck, and what is the probability or the likelihood that he is having meningitis. We are given some prior information that probability of having meningitis is 0.001, and the probability that a person having meningitis will be having stiff neck is 0.8, and probability that a person not having meningitis will have a stiff neck is 0.01. With this information, we are calculating the probability of a person having meningitis given that he has experienced stiff neck. So using the Bayes rule, we calculated this probability. This is where we can make inferences. Another example is that you have some prior knowledge about an event that what is the probability that a day will be sunny is 0.8 and it will be a rainy is 0.2. Now, for a particular day, you observed dryness in the environment or you observe the wetness in the environment. Now, your goal is to tell how likely is that the tomorrow will be rainy or it will be sunny based on the present day's information. So, what is given here that the day was wet, what is the probability that it will be sunny is 0.1. The day was observed to be dry, what and the day will be sunny next day is 0.9. Similarly, wet rain 0.7, dry rain 0.3 is this is the conditional probability we are given. Now our job is to find what is the if probability that a particular day will be experienced when the today's environment is dry. So dry will be due to the sunny. It will be today will be due to, now we will calculate how likely that if today is dry and tomorrow will be sunny, and if today is dry, tomorrow will be rainy. So probability of this thing, if we use the Bayes theorem again and using the total probability law, we can calculate that the probability that if we experience dryness, then next day will be sunny is 92.3%, and probability that today is dry, tomorrow will be rainy is the 0.077, which means around 7.7%. So this is how we make inferences with the Bayes theorem. The same thing goes to the example of email classifiers in the Gmail or any other, or you can make your own classifier or a filter to do some particular task to make inferences. Now, certain things we need to keep in mind is that these models are probabilistic in nature. These are probabilistic models. They may make mistakes, so we should not blindly rely on those things. We should try to check the facts also. And the models are always a realization of a certain process. They are the simplifications. They may not account all the variables and the interaction between the variables. So these things we should always keep in mind before actually building a model or applying a model. So they may not provide always the exact information. They are just the realizations. So with this, you can build your own classifier known as the Bayesian classifier. In modern day, it has given rise to a new tool or new kind of branch of statistics and artificial intelligence called the Bayesian statistics or Bayesian analysis, where based on some prior information, you update your beliefs about a particular process. One interesting case to study was a flight. A flight got missing in 2009, June 2009, and the flight was carrying some passengers. The Air France flight AF447 disappeared during a stormy weather, and it lost connection at certain point with the radar connection, and only the last known position about that flight was known, and its expected trajectory was also given. Now after 2 years of successive 2 years of after 2 years of search, the people were unsuccessful in locating the wreckage of this Air France flight which got missing. The only information was the last known location in the intended path and some search paths over which the flight was not found. So after 2 years of unsuccessful search, the authors of this paper were asked to build a model so that we can effectively search to locate the wreckage of that flight to retrieve the information. Now the authors used the information given and they build a probabilistic model for this flight model, and they had some intended flight path criteria. Intended flight path was given and the last known location was given, and it was given that where the flight can go on a radius, a circle of certain radius was given. Now the authors of this paper say that they constructed a probabilistic model to locate the the wreckage of that flight. They successfully built a model, and with that model they were able to locate the wreckage of that. There were certain improvements in the model because the prior information was not correct. That is, they were believing that the sensors of that flight were working and they can send signals, but it was found that they were not working, the batteries were dead. So they built a probabilistic model, and with that they were able to retrieve the flight, and the whole thing is based on the Bayesian analysis, Bayesian statistics. So with that information they designed certain paths and over which the flight was located, the wreckage of that flight was located. So Bayesian analysis is very important from the point of view of making inferences, and your system, your mobile phone is making those inferences. Maybe it's due in the email classification or the spam filtering or any other task. You can build it based on that you provide some information. So if you want to build a classifier, you can use the Bayesian classifiers as a choice, a tool for your analysis.